Charles' law is an experimental gas law which describes how gases tend to expand when heated. A modern statement of Charles's law is: when the pressure on a sample of a dry gas is held constant, the Kelvin temperature and the volume will be directly related. This directly proportional relationship can be written as or, where V is the volume of the gas, T is the temperature of the gas, K is a constant. This law describes how a gas expands as the temperature increases. Conversely, a decrease in temperature will lead to a decrease in volume. For comparing the same substance under two different sets of conditions, the law can be written as: the equation showed that, as absolute temperature increases, the volume of the gas also increases in proportion. The law was named after scientist Jacques Charles, who formulated the original law in his unpublished work from the 1780s. History: it was first published by French natural philosopher Joseph-Louis Gay-Lussac in 1802, although he credited the discovery to unpublished work from the 1780s by Jacques Charles. The law was independently discovered by British natural philosopher John Dalton by 1801, although Dalton's description was less thorough than Gay-Lussac's. The basic principles had already been described a century earlier by Guillaume Lemontens. Gay-Lussac was the first to demonstrate that the law applied generally to all gases, and to the vapors of volatile liquids if the temperature was more than a few degrees above the boiling point. His statement of the law can be expressed mathematically as: where V100 is the volume occupied by a given sample of gas at 1000 degrees Celsius. VO is the volume occupied by the same sample of gas at 0 degrees Celsius. And K is a constant which is the same for all gases at constant pressure. Gay-Lussac's value for K was 102.6666, remarkably close to the present-day value of 102.7315. This law was first given by J. Charles in 1787. Relation to absolute zero: Charles's law appears to imply that the volume of a gas will descend to zero at a certain temperature or at 273 degrees Celsius. Gay-Lussac was clear in his description that the law was not applicable at low temperatures. But I may mention that this last conclusion cannot be true except so long as the compressed vapors remain entirely in the elastic state. And this requires that their temperature shall be sufficiently elevated to enable them to resist the pressure which tends to make them assume the liquid state. Gay-Lussac had no experience of liquid air, although he appears to believe that the permanent gases such as air and hydrogen could be liquefied. Gay-Lussac had also worked with the vapors of volatile liquids in demonstrating Charles's law, and was aware that the law does not apply just above the boiling point of the liquid. I may however remark that when the temperature of the ether is only a little above its boiling point, its condensation is a little more rapid than that of atmospheric air. This fact is related to a phenomenon which is exhibited by a great many bodies when passing from the liquid to the solid state, but which is no longer sensible at temperatures a few degrees above that at which the transition occurs. The first mention of a temperature at which the volume of a gas might descend to zero was by William Thomson in 1848. This is what we might anticipate, when we reflect that infinite cold must correspond to a finite number of degrees of the air thermometer below zero. Since if we push the strict principle of graduation, stated above, sufficiently far, we should arrive at a point corresponding to the volume of air being reduced to nothing, which would be marked as a 273 degree of the scale. And therefore a 273 degree of the air thermometer is a point which cannot be reached at any finite temperature, however low. However, the absolute zero on the Kelvin temperature scale was originally defined in terms of the second law of thermodynamics, which Thomson himself described in 1852. Thomson did not assume that this was equal to the zero volume point of Charles's law, merely that Charles's law provided the minimum temperature which could be attained. The two can be shown to be equivalent by Ludwig Boltzmann's statistical view of entropy. Relation to kinetic theory: the kinetic theory of gases relates the macroscopic properties of gases, such as pressure and volume, to the microscopic properties of the molecules which make up the gas, particularly the mass and speed of the molecules. In order to derive Charles's law from kinetic theory, it is necessary to have a microscopic definition of temperature, This can be conveniently taken as the temperature being proportional to the average kinetic energy of the gas molecules, EC. Under this definition, the demonstration of Charles's law is almost trivial. The kinetic theory equivalent of the ideal gas law relates picavolt to the average kinetic energy. See also Boyle's law, combined gas law, Gay-Lussac's law, Avogadro's law, ideal gas law, Hahn-Boyle. References. Further reading, Kra paragraph Nig, A. Grunzer 1/4 G. Eine Theorie der Gas, Annalen und der Physik 99, 315 €22, Bibcode, 1856 and p. 175 315k, doi, 10.1002/ANDP 18,561,751,008a. Facsimile at the Bibliothèque Nationale de France. Clausius, R., Weberdei op der Bewegung, Welche Currency Nennen, Annalen der Physik und Chemie 176, 353 €79, Bibcode, 1857 and p. 176 353c, doi, 10.1002/ANDP 18,571,760,302a. Facsimile at the Bibliothèque Nationale de France. Joseph Louis Gay-Lussac Liste des Communications. External links, Charles's Law Simulation from Davidson College, Davidson, North Carolina, Charles's Law Simulation from tutorvista.com, Charles's Law Demonstration by Professor Robert Burke, Carleton University, Ottawa, Canada, Charles's Law Animation from the Leonardo Project.